Hello, my name is Jeff Messier. I'm a professor of electrical engineering in the Schulich School of Engineering, and this is Module 6, Functions of a Random Variable. So as engineers, we're often dealing with systems, and as electrical engineers, we're often dealing with systems that process signals. And many times we can represent this system as a function. So we have some input signal x going through a system that we characterize by a function g, and the output y is equal to g with x as its argument. Now, of course, because this class is about randomness and probability, we're going to consider the case where the input of our system x is a random variable. Now, as you would expect, the output y is also a random variable, except it will have been altered in some way by the system that we're characterizing by the function g. Now, this means that its mean might be altered, its variance might be altered, and its actual PDF might be altered as well. Now, in earlier modules, we've seen already how we can calculate the mean and variance of y based on knowledge of the PDF of x. And so we know that the mean of y is the integral of the PDF of x, our input, multiplied by the function g. If we want the mean of the squared value of y, that squaring operator is just a modification of the function. It's almost like we do this to our system. And so the mean squared value is, again, the integral of the input of our PDF multiplied by the squared function, g. And of course, then variance can be calculated just by subtracting the expected value of the squared random variable minus the square of its mean. So we know how to do that already, and often that's all we need to do. However, sometimes it is necessary to determine the full PDF of y, particularly if we want to do things like determine the probability that y falls within a certain interval. And that's a little bit more complex, but that is also the focus of this module. In this module, we are going to look at different techniques for determining the PDF of y. The first way we can determine the distribution of y is using the CDF. So let's consider the situation where we have our system. X is our input. Y is the output. And we want to determine the probability that y is less than or equal to a certain value given by lowercase y. And of course, this is just the CDF. Right? This is what the CDF gives us. So the CDF of y is the probability that y is less than or equal to a particular fixed value. However, we can translate this condition back to the input by saying, so we already know that x, uppercase X, capital X, is equivalent to capital Y after transformation through the system. So all we need to do is take lowercase y, which is our constant, and translate it back to the input. And so the condition we have at the output is equivalent to saying what's the probability that x is less than or equal to the inverse of the function, where we've got lowercase y as our argument. So that's what we've written here. Now, we know that this probability, again, is the CDF probability, and so this is equivalent to the CDF of x, where we replace our argument x, our argument lowercase x, with the inverse of our system function with lowercase y as its argument. So basically what you do is everywhere where you see a lowercase x in the equation for the CDF of x, you replace it with the expression for the inverse function with little y as its argument. And then you can find the PDF of y just by taking the derivative of this expression. And again, we're taking the derivative with respect to lowercase y because all instances of lowercase x have been replaced by the inverse function. And then we end up getting using the chain rule for differentiation, we have the PDF of x with the inverse function as replacing all instances of lowercase x multiplied by the derivative with respect to y of the inverse function with little y as its argument. Okay, so let's illustrate how this works using a few examples. For the examples that we're going to do in this module, we're going to assume that our input random variable x is exponentially distributed with a PDF given as follows. And the first example we're going to do is a linear transformation of the input random variable. So our output random variable y is equal to the input random variable x multiplied by a constant and with an offset added to it. And this is a very, as you can appreciate, we work with linear systems all the time. Multiplying by a constant is just amplification or attenuation, and adding an offset is just translating a signal to a different level. So this is a simple but very broadly useful example. So you'll have noted in the slide when we talked about this general CDF technique that we work with the inverse function a lot. And so all the inverse function is just solving for the little variable x. So x is equal to y minus b over a. So the basic idea is to take the expression for the CDF of x, and everywhere where you find a lowercase x, you replace it with y minus b over a. Now, it turns out that we are going to have to consider two cases. For one case, for when a is positive, and the other case for when a is negative, because that will define different slopes for our line, and we have to treat them in a slightly different way. Let's consider the positive case first, which is what I've shown in the diagram on this slide. So remember, we're starting by finding the CDF of y, which is equal to the probability that the random variable is less than or equal to a constant represented by lowercase y. And so if we show this on our diagram, on our y-axis, this is the point equal to lowercase y, and everything less than or equal to it is the region I'm showing by highlighting it in red. Now, if we translate this across to the x-axis, this corresponds to the region. So this point x is equal to y minus b over a, and the region that we're interested in on the y-axis corresponds to this region on the x-axis. So the probability that y is less than or equal to lowercase, the probability that the random variable y is less than or equal to lowercase y is equal to the probability that the random variable x is less than or equal to y minus b over a, or basically the probability that it lands in this interval, which is just equal to the CDF for x with y minus b over a as its argument. Now, we also want to find the PDF, and in general we do want to find the PDF. We work with PDFs maybe a little bit more than CDFs. So the PDF of y is equal to the derivative of f of x with respect to y, with y minus b as an argument. Now, the derivative of y minus b over a is just equal to one over a, and this is the final expression. So all we do is we take the PDF of x, we substitute y minus b over a everywhere where we have a little x, and then we scale the whole thing by 1 over a. And so the final expression for the PDF of y is equal to this equation I've highlighted on the lower part of the screen. The only modification that we need to make is the region over which y is the PDF y is defined. So if I just blank my slide here, remember that our original PDF, the exponential distribution, was defined for positive x, which corresponds to this region on our diagram. Now, if we take our straight line and we translate the region I've just drawn to the y-axis, it maps to this region here. And so rather than our PDF being defined for x greater than or equal to 0, it's defined for y greater than or equal to b, which is the y-intercept of our line. So this, and this is kind of the reason why I use the exponential distribution as our example. We need to not only work with, the function part of the PDF, but if there are regions that our input PDF is defined on, we need to use our function, in this case our straight line, to translate those regions from the x-axis to the y-axis. So on this second page, this is the second part of the example where a is a negative number, so we have a negative slope on our line. Now we start out exactly the same way we did before. The CDF of y is equal to the probability y is less than or equal to, the random variable y is less than or equal to lowercase y, which corresponds to exactly the same region on the y-axis. However, when we translate this region over to the x-axis, it corresponds to this positive going region here, starting at lowercase x, which again is equal to y minus b over a. So the region we're interested in starts at the same point, but now it goes off to the right rather than going off to the left. And so the probability that the random variable y is less than or equal to lowercase y is actually the probability that random variable x is greater than y minus b over a, which we can still express in terms of the CDF of x, but it's 1 minus f of x with y minus b over a as its argument. So now to get the PDF of y, we do it exactly the same thing. We take the derivative of our expression with respect to y. Of course, the derivative of 1 with respect to y is equal to 0. And so we essentially get the same expression that we had before. The only difference is that we scale by negative 1 over a, which essentially cancels out the negative value of a itself, right? Because in this case, a is negative. And that's important because remember, PDFs always have to be positive. So if you multiply a PDF by a negative number, then somehow you've made a mistake somewhere. And so our expression for our final PDF is negative alpha over a, but that's fine because that negative is canceled by the negative value of a, the exponent of minus alpha y minus b over a. And then just blanking out the slide again to talk about the region of convergence, I kind of need to extend my diagram a little bit here. But this is the y-intercept b up here in this case. Now remember, our input PDF was defined for positive x. When that's translated to the y-axis, it's actually the region the PDF of y is defined for starts at b and then goes negative. So in this case, our PDF is defined for y less than b, less than the y-intercept of our line. And here are some pictures of the resulting PDFs. So here I show the input PDF f of x and the output PDF f of y for two cases where a is positive and a is negative. And for this example, I've used lambda equal to 1, a equal to plus or minus 2, and b equal to 3. And in many cases, when you're dealing with functions of random variables, you can look at your PDF and you can just ask yourself, okay, does this make sense, right? So first of all, let's consider the case where a is positive, so a is equal to positive 2. So we're multiplying our random variable by 2. So we're amplifying it, or we're increasing the range of our random variable, if you like. And so rather than decaying quickly, like the blue line, the red line decays much more slowly. And that makes sense because the values have been amplified. The values are larger and they should spread out over a broader range. We've also added a constant value equal to 3 to our PDF, which has shifted the PDF from 0 up to the number 3. Also completely makes sense, right? Because we've just added 3 to all the values, so we would expect our PDF to translate to the right. Now, the case where we multiply by minus 2, we flipped everything stays the same, except we flipped our PDF around. It's now negative going, which again makes sense because we had exclusively positive values, then we multiplied it by a negative number, which gives us exclusively negative values. But then we added positive 3 to them, which translated the PDF to the right. And so this is an important thing to remember. Once you've done this function of a random variable stuff and you finished your calculation, take the time to plot the PDF and just look at it and say, okay, does my result make sense? Okay, let's consider a nonlinear example now where y is equal to x squared. So the inverse function, little x, is equal to plus or minus the square root of y. So there's actually 2 solutions to this function rather than 1. Now, we start off exactly the same as we always have. The CDF of y is equal to the probability that y is or the random variable y is less than or equal to lowercase y, which is this point on the x-axis. But in this case, we know that we can't go negative, right? Because y is a squared value, so y always has to be positive. And so our region of interest corresponds to just this region here. And we have to translate that into 2 directions because of the 2 solutions for our inverse function. So the probability that y falls into this region is equal to the probability that it falls into this closed region on the x-axis, bounded by the 2 solutions of our inverse function. So the probability that the random variable y is less than or equal to lowercase y, is the probability that the random variable x is less than or equal to positive root y, but greater than or equal to negative root y. So this is the first time we've seen a closed interval, but it's not a problem for us because we can still express our probability in terms of the CDF of our input x. So this is just equal to the CDF with argument positive root y minus the CDF with an argument negative root y. And so it doesn't matter if we have the CDF of x show up a couple of times here, we can still take the derivative and still proceed as we always have. So we take the derivative of this expression with respect to y in order to find our PDF, and then we just have 2 terms. So we have f of x with positive root y as our argument, f of x with negative root y as our argument, and then we just have 2 different scaling factors out front. And so we're given, I'm sort of obscuring it here, but this is the final expression for this is the final general expression for the PDF of y. And so, blanking out the slide, let's talk about our region of convergence. So our input PDF, or the region over which our PDF is defined, the region our input PDF is defined is for all positive values for x, using our function that translates only to positive values of y. If we give our PDF the argument negative root y, then that causes it to go negative. So this term, for this particular example, drops out, and we just have this as our final expression for our PDF, defined as for y greater than or equal to 0 and there should be a 2 under there. That's a little bit of a typo. And so here's a picture of our PDF of x and our PDF of y. Again, assuming lambda equal to 1. And this PDF also makes sense. So a squaring operation is a nonlinear operation, so it tends to make very large values even larger and very small values even smaller. And we see that in the PDF of y. So we get a spreading out of our PDF. We get much more extremely large values, and we get many more extremely small values. There is a second technique for finding the PDF of y directly using a generalized formula. So let's assume that we have the possibility of having several solutions for our equation, y is equal to g of x. And so let those solutions be denoted as xk. And then the PDF is just calculated by the summation over all possible solutions to our function g, f of x with the argument xk divided by the absolute value of the derivative of our system function with xk as an argument as well, where n is the number of solutions for our system equation. So let's do some examples and it'll be a lot more clear exactly how this formula works. Okay, so let's redo our first example. Y is equal to ax plus b. Our function y is equal to g of x, which is equal to ax plus b, and it has only one solution. x1 is equal to y minus b over a. The derivative of the function g is, with respect to x, is just equal to a, and we take the magnitude of that, which is equal to the magnitude of a. And so our expression for the PDF of y is equal to the PDF of x with x1, our first solution for our equation, as its argument, divided by the derivative of the system solution with respect to x, again with x1 as its argument. And so what we end up with is f of x with y minus b over a as its argument, which is exactly what we had with the previous expression, divided by the magnitude of a. Now, the magnitude of a is nice because this magnitude operator takes care of the problem with a positive or negative value of a. So the only difference in our previous example between the positive and negative slope was that the negative solution had an extra negative sign to get rid of the negative slope. But in this case, we have the magnitude operator. So it's not too hard to see that this expression encompasses both of our positive and negative slope cases for the linear transformation in the previous example. In the second example, y is equal to x squared. The system function g of x equal to x squared has two solutions. x1 is equal to root y and x2 is equal to minus root y. The derivative of the system function with respect to x is 2x. And so then, since we have two solutions, we have two terms in our summation. F of x with x1 as its argument plus f of x with x2 as its argument, and the derivative also with x1 and x2 as its arguments. So we have f of x with the first solution as its argument, f of x with the second solution as its argument. The magnitude, since we're taking the magnitude, we get rid of the negative sign, and in both cases our denominator is equal to 2 root y. So this is a second method that you can use to kind of check your work. Again, this is, seems like a slightly more efficient method, but you do still have to be careful when you define the regions over which your PDF is defined. You still have to sort of, what I usually do is just draw out the function and make sure that I've got those regions correct.